In this lecture, we're going to introduce AI-controlled movement. So we're going to have a look at actually a number of reasonably simple algorithms known as kinematic steering algorithms, which will help a character move about within an environment. We'll build upon this in some of the later lectures to introduce somewhat more sophisticated forms of movement that will enrich the ability of our AI-controlled characters to move around within their environment. Just as a reminder, in terms of artificial intelligence, movement was one of these basic behaviors that we want to quite often impart to our AI-controlled entities. And on top of this, then we can get into aspects like decision making or up to tactical or strategic analysis. But very much, AI movement is the basic form of AI for a lot of our characters. When we think about moving about within an environment, in essence, what we need to have is input about that environment or input about how we want to move. An algorithm will then process this, and as output will then provide directions or instructions to that character about how it should move. So we might give it a target location, and it might consider its surroundings, whereabouts it is, where the target is, and then give you the direction in which the character should travel to move it towards or the target overall. We'll start off looking at some very simple algorithms that only really are concerned about where you're at and where you want to go to, and we'll increase that up to more sophisticated ones that also take into account, what is around you. Obviously, what is around you will either aid or impede your ability to move. But the first forms of algorithms that we'll look at won't be concerned about that. They'll assume it's almost an open environment like space where you can move in any old direction that you fancy. When we're thinking about the output, we'll start off looking at kinematic algorithms, and they will give us a velocity as output. So that will be a direction and a speed. They'll say move in this particular direction at that particular speed. Alongside this, you have also other approaches known as steering algorithms, or dynamic ones as well. They output an acceleration, which is a change in direction and speed. So the kinematic ones will be sort of a sudden, abrupt change in velocity. They'll change immediately. For the steering algorithms, the ones that output an acceleration, you'll have a smooth change in velocity due to the accelerative forces. For us to do this, for us to give an object to have the notion of velocity, to have a position and orientation, we're going to have to introduce a number of different variables within our programs. And that, for game objects, will help determine whereabouts it is found, how it's oriented, and also how it moves through the environment. And off the screen here, you can see down at the bottom that we will have to go to our game objects if we're interested in getting them to use kinematic steering, and to put in, at the very least, a position and an orientation, a velocity, and a rotation. You can see that the position is described as a vector. So in 2 dimensions, we'd have an X and a Y. In 3 dimensions, we'd have an X, a Y, and a Z. And the position is whereabouts it is located in our game world relative to some defined origin. The orientation is stored as a float, and we normally assume this is the number of degrees or radians that it is rotated around from some default reference point. And it differs just depending on convention. Sometimes, by convention, 0 degrees is pointing along the x-axis, or it can be pointing straight up the y-axis. A positive rotation is something that moves in a clockwise rotation. A negative rotation is something that moves in an anti-clockwise direction. So when we talk about the orientation, this is the direction in which that object is facing. And when we talk about a rotation, this is the speed at which that orientation is changing, so the speed at which it is rotating around. Small aside, so quite often in maths, or most mathematical textbooks, when you're looking or thinking about how something is oriented, you will describe its angle, if you like, using radians. So 360 degrees is the same as 2 pi radians. So radians is the normal convention that's used. In Android, for a lot of the methods where they're talking about angles and things like that, they actually use degrees. So it will be from 0 to 360 degrees, which I suppose, makes sense in terms of ease of understanding, but we'll do a little bit of trigonometry in this, and trigonometry will give us output really in terms of our radian values. Now, for the steering algorithms, as a reminder, these are the ones that will output an accelerative force. We have to have a way then of updating our velocity. And for both the steering and for the kinematic approaches, we need to have a way of updating our position and orientation using our velocity and rotation. And you can see over here the simple forms that we're going to use it. Now, these are using simplified Newton-Euler equations. There is actually a time squared component in this for the acceleration. But if you are running at a reasonably high number of frames per second, the time interval, is small, and if you square a small number, you get an even smaller number. So basically, you can effectively ignore the thing. But in essence, what we will do for updating our game objects is that if we have an acceleration, because it's a steering algorithm, we'll multiply this by the time delta, how much time has elapsed for this frame. So if we're running at 20 frames a second, we'll multiply our acceleration, which will be a change in velocity per second, by 1/20th, the amount of duration of that frame. And we'll add that on then to our velocity. We'll do exactly the same for the angular acceleration. We'll add that on to the rotational velocity. And equally, we'll look at the velocity that we have, how much time has elapsed for that frame, multiply those two together and add it onto the position. This will give us our new position for that frame. And we'll look at our rotation, again scaled by the duration of the frame, and we'll use that to update the orientation. So it'll have a new orientation within our game world. And that's how we'll update each of our objects, each frame, so that it does have a new position and new orientation within our world. We'll start off looking at the kinematic movement algorithm. We're only going to consider a few of them, and we'll do it reasonably quickly because we're going to use this as a staging post to move on to looking at steering algorithms, which are more interesting, and there's a richer collection of them that we can use therein. So for kinematic movement, they operate using positions and orientations. Fair enough, this is the other one. And the output from this will be a specific velocity and a specific, a direction and an orientation. We'll get both of these things output directly from it. So that it'll change the velocity instantaneously, effectively. And for us, when we're thinking about these algorithms, you go to the question then of, okay, if you have a velocity, so it's a speed in a particular direction, what control can you have over the speed? Now we can have 0, not moving, up to some defined maximum speed. So we have the notion that most objects have a defined maximum beyond which they are not able or not permitted to move faster than. We will look at seek, we'll look at flee, and flee is really the opposite of seek, and we'll look at arrive. To give you 3 examples of the types of algorithms that we can embed within kinematic movement. So seek will be moving towards a target point, flee will be moving away from that target point, and arrive will be moving towards some target point, but you want to stop whenever you arrive at or reach that target point. Let's have a look at seek first of all. So seek inputs a current and target location, that is it. It needs to know whereabouts you're at, where you want to go to. That's the only thing that it is. And it's going to calculate the direction from the current position to your target position. So that's the direction in which we want to travel. And the velocity that it will output will include that direction moving at the defined maximum speed that object is allowed to move in. So for example, you can see the diagram over on the right hand side. Our current velocity may be pointing up the screen. We're heading towards the green plus. So if we were to seek towards that, our new velocity is going to be heading directly towards it in the maximum speed that we have available for that object. A little fragment of, it's kind of pseudocode at the bottom, so it's not necessarily directly convertible into Java, but more or less the information that is there. So we'll call seek, we'll pass in a vector saying, well, whereabouts we're at. We'll pass in a second vector saying, where do you want to go to? We'll pass in a scalar value, a simple float for the maximum speed. That's how fast we're permitted to travel in any particular direction. And the key line that we have after it is the velocity vector is equal to target minus source, normalized times maximum speed. Now we'll break that down. It probably would break into maybe 3 lines of actual code, but for reasons of space getting it all on one slide, I put it all together into one. But there's 3 steps within this, and they're all logical steps. The first one is target minus source. So target is the destination point. Source is the where you're at point. And if you were to take the target point and take away from that the source point, what you get is a vector that starts at where you're at and goes all the way to where you want to go to. So effectively it is the line between your current position and your target position. That particular line, that vector, is what target minus source takes away. Now, we can normalize any vector simply using Pythagoras' theorem to work out the length of it and then dividing the x and the y by those components. If we normalize a vector, it keeps the same direction of travel, but it scales back its overall length to be of length 1. And that's important because in normalizing it, we don't change the direction we're going in, but we give everything the same fixed length of length 1. So target minus source normalized means that we have a vector of length 1, it's a unit vector, pointing towards the target where we want to go to. And the reason we do that then is that's the direction we want to travel in, but we want to set the speed in which we travel to our maximum speed. So after we've normalized the vector, we multiply it by the maximum speed. So that effectively will take a long vector, shrink it down to size 1, and then increase it up to the maximum speed. So we've got the right direction and we've got our maximum speed. That's what we return, and that is the output from seek, simple as that. There's a little bit the determine orientation on the other side. So depending on how you're updating your object, you will have a velocity that you're moving in. If you wanted to update the orientation so that you point in the direction of travel, and quite often you want the character to point in the direction that the character is traveling in, then there's a method determine orientation shown over here that will do that. It takes in the velocity, so this is the speed at which the object's moving, and it takes in the current orientation, how you are currently orientated within the world. And there's a small check there that if the length of the velocity, so the length of the velocity is basically your speed, if it is equal to 0, so if you're not moving, in that sense you return the current orientation, you don't try to change. And that's just basically a safeguard in case we were to call this with 0 speed, which doesn't have any defined orientation due to movement. Otherwise, then this is the return bit at the bottom, which is the key bit. We are going to return it's a mass function, it's called arctan2, and we're passing in the x and y components of the velocity, and we're going to look at that on the next slide. But in essence, that will return an orientation that points us in the direction of travel, but we'll talk a little bit more about that in the next slide. Flee then is the opposite of seek. So as opposed to having a current location, a target point, and moving towards it, we move directly away from it, we flee from it as far as we can. So it is the opposite of seek. It's incredibly straightforward. The equation, if you look at flee down there, again, we take in a source, a target, and maximum speed. At first glance, you could sort of glance at that and think, hold on, exactly the same. It's nearly exactly the same. How it differs is it is source minus target, as opposed to target minus source. So there we get a vector not to the target location, but a vector pointing away from the target location. And by doing if you sort of did a piece of paper and sort of source minus target, target minus source, you'll see that the vector is the same length, just in opposite directions. We return the velocity there using the same operations. That will cause us to move away at full speed from the target location. So it's reasonably straightforward. Now, the little side on arctan2, if you think about a velocity, it has an x and a y component. So I can be moving at a certain direction on the x axis and a certain speed in the x axis and a certain speed in the y axis. And if I wanted to work out the angle that I'm moving at, Then it goes into trigonometry. For using the tangent of an angle, we could opposite over adjacent. So I can use the y and the x component, and that using tan or arctan will give me the angle that I'm moving in. But hopefully you'll recall that for sine, for cosine, for tan, it's cyclic. It repeats with a certain period, and the period is every 180 degrees is going to repeat around at the start again. Other way of thinking this here, so if 2 pi radians is the same as 360 degrees, then pi radians is the same as 180 degrees. So what you can see there, it computes the arctan 2, computes the arctangent, the inverse tangent of y over x, opposite over adjacent, in the range of minus pi to pi, which is minus 180 degrees to positive 180 degrees. We need this because the basic tan is cyclic at 180 degrees. So every 180 degrees it repeats, which means we're missing half of our 360 degree scale. So the normal arctan function returns in the range of minus pi over 2, which is minus 90, to pi over 2, which is 90. So if we want to have full 360 degree motion, we have to use arctan 2. The final one we're going to have a look at is arrive. And arrive is a variant of seek. So a limitation of seek is that it will head towards the target at full speed and then overshoot the target. And then it's going to head back towards the target in the opposite direction at full speed and overshoot the target, and then to repeat that process. So if we want to arrive at a certain point, we don't want to be necessarily hitting it at full speed. We want to slow down as we get closer to it and then stop once we've arrived at it. And that's what arrive does. So it's an extension then to our basic seek behavior. So there's an example we can see down at the bottom, where if we're far away, our velocity will be the maximum speed we can travel at. But once we get sufficiently close, and we need to define what sufficiently close is, then we're going to scale our velocity back so that it reduces down to some stopping velocity. And when we get sufficiently close, and again we need to define what that is, to our target, we'll simply stop. So there's a couple of, if you like, trigger points where we start slowing down, and a trigger point for where we will stop. So there's the arrive function here. We're taking in again our source, where we're at, our target, where we want to go to, our maximum speed, which is the speed at which we maximum speed at which we can travel, and our near radius. So we're going to use this for triggering whereabouts we actually will start slowing down. First line, we have a slowing factor. So basically this is something as a parameter we can use within this here to control how quickly we slow down. Is it going to be a linear descent? Is it going to be a stronger one than linear? So this is basically the strength at which we're going to be braking and reducing our speed. So initially we start off with a velocity of 0. So there's 0, 0 there. So if it's 2 dimensions, x and y will be 0. 3 dimensions, x, y, and z will be 0. So our default starting position is that we will return a value of 0. We've reached our point. That's where we're starting at, our default assumption. Work out our separation vector then, same as before, target minus source. So this will give us a vector from where we're at to where we want to go to. So there, if we take the length of that vector, that is the distance we are away. And if we normalize that vector, that is the direction of which we're going to travel. So we then say if separation.length, so this is the length of the vector from where we're at, where we want to go to. In other words, how far away in a straight line movement are we from our target destination? And if it is less than the near radius, so in this sense we are saying that we have reached or sort of sufficiently close radius. So in this sense we're sufficiently close to the object that we're happy that we've reached it. And we put this in because we don't want to precisely reach the point, because you'll have a little bit of jitter then just around it. But whenever we get sufficiently close to it, we're going to say we're sufficiently close to be able to stop. So if the length of our separation from source and target is less than the near radius, then we return velocity. And that'll be the default one we assigned. It'll be a value of 0. So in this sense, we'll simply have determined we've reached our destination and we stop. The bit underneath that then says that, okay, velocity is equal to separation divided by slowing factor. So it takes the total distance that we have and divides it by the slowing factor. Now this is going to give us notionally a target velocity. And the target velocity is going to increase as the separation length increases. So velocity is equal to separation. So the bigger the separation, the bigger the velocity. We divide it by our slowing factor, and this is the thing then that controls how quickly we slow down. So a slowing factor, for example, this is 0.2. So actually we're going to be trying to accelerate quite a significant bit until we get reasonably close to it. That gives us our target velocity. And you can see under this here, velocity.length is greater than max speed. So in working out our target velocity, we might end up saying, well, ideally we would like to be moving to this object at a speed faster than the object is allowed to move towards it, so greater than the max speed. So by checking the length of the velocity, how fast we want to move, if it is greater than the maximum speed, we need to then reduce it back to the maximum speed. If it's less than our maximum speed, that's fine. We let her travel to it towards that particular calculated speed. But let's assume that velocity is greater than the maximum speed. In that sense, we normalize the velocity. So that keeps the same direction, but reduces it down to length 1 of unit length. And we multiply that by the maximum speed. So we did the same sort of thing when we were looking at the seek algorithm. So that will give us the right direction at the maximum speed, and we'll head in that particular one. Very bottom, we return the velocity that we've calculated, and that will simply be it. If we run this algorithm, whenever it gets sufficiently close, it'll stop. Beyond that, based on the slowing factor, it's going to slow down as it gets closer to it. And if you wanted to, the slowing factor, you probably would want to actually pass it in as a parameter to the method as well. So you have more control over how the thing is slowed down. Key takeaways, a couple of them. AI-controlled entities often need some way of moving about their environment. It depends on what type of AI you're talking about, but for a lot of them, we do want them to move around their environment. And for kinematic algorithms, which I put at a velocity, they give us the sort of basic way in which we can move around. But we want to build upon this in the later lectures to look at accelerative forces and then more fancy forms of steering within our environment.